Hello, I'm Dan Boniciolli and welcome to ChemSkills Podcasts. This is podcast number 15 in the series, and the topic of this session is analysing mass spectra. As we saw in podcast 14, the mass spectrometer is a device that differentiates between particles on the basis of their mass. The very first stage involves ionisation, and ionisation occurs as a result of electron bombardment. Now, if a particle such as this, the pentane molecule, were to be inserted into the ionisation chamber, electron bombardment would knock out any one of these electrons involved in bonding, causing eventually that bond to fracture, producing two different fragments. Now, electron bombardment would knock out one electron, but it would leave the other electron behind to either stay with the methyl group, in this particular example, or remain with the butyl group. Now, if the electron stays with the methyl group, the butyl group becomes an ion because its electron has been knocked out. If the electron stays with the butyl group, then the methyl becomes a fragment ion. Whichever ion forms, that's then attracted to the next stage in the mass spectrometer, the acceleration region, and eventually goes through the mass spectrometer, appearing on the detector as a spike on a graph. Now, here's an animation that shows what happens. So as you can see in this animation, and we'll have another look at that, the electron remains with the methyl group. The butyl becomes an ion of molecular weight 57. Now, as soon as that ion forms, that fragment ion then gets attracted into the acceleration chamber, the next chamber in the mass spectrometer, and moved away from the ionisation chamber. The methyl fragment remains behind, and that can be bombarded further and further ionised. So what would happen then would be that when the 57 molecular mass fragment for butyl reaches the detector, we would see a spike occurring at a point on the graph corresponding to a molecular weight of 57. And that spike would represent the butyl ion that has just gone through the mass spectrometer. But what's left behind is the methyl group, which has a molecular weight of 15. And the separation from 72 to 57 is equal to the weight of the methyl fragment. 72 is the weight of the original molecule, or, and to be absolutely correct, the weight of the molecular ion. 72 is the weight of pentane, and an intact pentane molecule could become ionized with the removal of an electron due to bombardment, and then a whole pentane molecule could go through the spectrometer, so in which case we'd get a spike at 72. This is the molecular ion peak. But the separation between these two peaks is indicative of what's left behind in the ionisation chamber. Now, alternatively, electron bombardment could occur at another point in the molecule. So in this case, it'd be the second bond down the chain, causing fragmentation. If the electron remains behind with the ethyl group, then as we saw, a propyl fragment ion would form, and the propyl fragment ion would then move into the next part of the mass spectrometer and eventually be detected on the detector. One more time, the propyl ion that would form has a molecular mass of 43, and so on the graph, which already has a spike at 72 for the molecular ion, a spike at 57 for the butyl ion, we would now find a spike at 43 for the propyl ion. Now, the difference between 43 and 27 and 72 rather, is 29, which is the weight of the ethyl fragment or ethyl radical that's left behind. Now, this is called a radical because it has an unpaired electron. Alternatively, we could find collision electron bombardment that causes the electron this time to remain with the propyl fragment, in which case we would get an ethyl ion forming, an ethyl ion that has a molecular weight of 29. One more time. And then as soon as that ion forms, it moves on to the next part of the mass spectrometer. So what we would get on the spectrum would be all the previous spikes that we saw, but now in addition, a spike of 29. Now what would be left behind would be a molecular fragment, the propyl fragment, which has a molecular weight of 43. And finally, electron bombardment of the first bond could cause a butyl radical to be left behind, but a methyl ion to form. So this time the electron remains with the butyl part, and the methyl ion that forms with a molecular weight of 15 would then be accelerated through to the next part, eventually being detected on the detector. And so what we'd have is a graph showing the appearance of the peak at 15, representing the methyl group. 57 is the molecular weight of the fragment that's left behind, the radical that's left behind in the ionization chamber. And again, that can be ionized further, and fragments from this can then appear on the spectrum at a later point. So we end up with a mass spectrum for pentane that could very much look something like this. And by looking at the spectrum, we can see all the various possibilities for the breakdown of the molecule as a result of electron bombardment. Now, some of the terms that we've used so far include molecular ion. Now, the molecular ion is the ion obtained by the loss of an electron from the entire molecule. The molecular ion is the peak, the furthest most peak to the right on the mass spectrum. This is the molecular ion peak. So in this example, the molecular ion is represented by this peak at a molecular weight of 108. The base peak is the peak that is assigned an intensity of 100%. So that would be this peak here at a molecular weight of 79. So this is the most common fragment, in other words, and that's called the base peak. So that's given an intensity of 100%. M plus is a symbol that we often use for the molecular ion. The radical was a species with an unpaired electron, and that is very often the fragment that's left behind in the ionization chamber. The fragment ions are the cations that form as a result of the breakdown or decomposition of the molecular ion due to electron bombardment. These correspond to stable carbocations. Now, some common fragments that are required by the IB syllabus include things like, as we've already seen, the methyl ion with a molecular weight of 15. From pentane, we could also get an ethyl ion with a molecular weight of 29. From a molecule like this, butanoic acid, it's not uncommon to get a hydroxyl ion, an OH plus with a molecular weight of 17, so that bond there would fracture, or alternatively the entire carboxyl functional group could be ionized and move through the spectrometer. So in that case, this bond here would fracture. The carboxyl has a molecular weight of 45. And finally, a CH2OH group could be released from this molecule with the fragmentation of that bond. And so this ion could form the CH2OH, and that would then move through the mass spectrometer, or an OCH3+. So this section here could fracture. So in this ester, the methyl component of the ester here could break off and move through the mass spectrometer. Now, there are many other fragments possible. It's just what I've tried to do is identify the ones that the syllabus requires that students be familiar with. And so these numbers, fragment ions of 15, 29, 17, 45, and 31, can be used to identify molecules. If these numbers appear on a mass spectrum as either a spike or as a separation from the molecular ion, then it gives us an idea of as to what was on the molecule. So let's have a look at a typical question and see how we would unpack the spectrum to try to work out what the substance is. This question has been slightly modified so that it's appropriate for this podcast. But it includes an organic compound with molecular formula C3H8O, has two structural isomers A and B with the same functional group. The mass spectrum for isomer A is shown. So what we'd do is we'd look at the spectrum and we'd try to identify some characteristic peaks or some characteristic separations. So one of the first and most obvious separations here is a separation of 15 from the molecular ion peak of 60 to this first peak of 45. 15, and that, as we've seen previously, corresponds to a methyl group. Another, from 31 to 60, is a separation of 29, and that corresponds to an ethyl group. When we look at some of the spikes, a spike of 31, which was the CH2OH plus fragment ion, and a spike of 29, which was the ethyl fragment ion. Now, looking at all of these fragments and separation, it's fairly clear that the molecule must have a combination of, or a pattern of CH3CH2, because otherwise this ethyl group would not be possible, or this ethyl fragment would not be possible. So for this compound that has only 3 carbons and an oxygen, it's fairly obvious that the compound must have a chain of at least 2 carbons, and with this fragment ion we can see that the hydroxyl group is the functional group, and the hydroxyl group is attached to a carbon, so that must be the 3rd carbon. Subsequently we arrive at this formula, this structural formula for isomer A, with the hydroxyl group attached to the CH2, so you get that CH2OH fragment. There would be the ethyl fragment. Here's the methyl fragment that we saw on the mass spectrum. So this mass spectrum could very well be formed from this molecule, 1-propanol. Mass spectrum B, again we go through the process of identifying the key spikes or separations, and we find that there again is a separation of 15, which is a methyl group. There's also a separation of 17 from 60 to 43, which is the OH functional group, the hydroxyl functional group. There is also a spike at 15, which was our methyl fragment ion. But most characteristically, the absence of an ethyl functional group, or of an ethyl fragment or ethyl separation occurring at what would be 29. Now, the absence of that suggests that this molecule does not contain an ethyl component. And so on this basis, we can assume that isomer B, which obviously has the same functional group as isomer A as stated in the original question, must have the hydroxyl group off that middle carbon. And so you can see from this molecule there'd be no way that we could break a bond and result in an ethyl fragment being produced. So this would be the structural formula for isomer B, 2-propanol. Okay, well that brings me to the end of this podcast. Thank you for listening. I hope that was clear enough. Please join me for future podcasts. Bye.